Okay. And I think we basically got here, right? So just kind of walking back through things real quick. We set things up and drew a diagram, right? This farmer has a barn, he's fencing in a rectangular plot next to it, so he's got to build those three sides. He's got a set amount of fence to use, which gives us this constraint equation, 2L plus W equals 180. That's sort of like how things are related, you know, and what we have to work with in the context of the problem. We're trying to maximize the area. Well, it's a rectangle, so area is length times width. The problem is that this has too many things I don't know, so what we want to do is reduce the number of things we don't know, right? What I can do is take this constraint or like perimeter equation, basically, solve it for either L or W. I solve for W because it's a little bit easier here, right? Solve for L, you'd have to divide by 2, which is fine, that works too. But I solved this for W, substitute it in here so that we get area as a function of just one thing, right? I labeled that thing L. The L part's not important, just some variable, but it's a function of one variable. We know how to deal with those. And in particular, it's a function of one variable that is quadratic because of the square term and opening down because that leading term is negative, right? So we have a quadratic that opens down that gives us the area. Everybody okay with all that? That's the quick recap of where we kind of ended up yesterday. All right, so what we have is, if we look at a graph of area as a function of length, we're looking at something that looks about like this. We only care about what happens in quadrant 1 because we're talking about area and side length, so the only thing that matters is positive stuff, right? And what are we trying to find? We want the maximum area. Well, where would the maximum area be? The top, the vertex, right? All right, so y'all went home and found the vertex of this thing, right? How do we get it? You could, so it's in standard form now. We could, you gotta go through the whole completing the square thing. It's gonna be a mess. Or we can graph it, but the numbers are way off and like, it's gonna be hard to find. Or quick version to find the vertex from standard form. Must be over 2a, yeah. Minus b over 2a. Here, everything's written in terms of L, so that would give us L, right? Negative b over 2a. What's b? 180, and a is negative 2, and 180 divided by 4 is 45. 45, yeah. Okay, so what did we just find? So we'll ask when to be negative. 2 things. One, there's a negative built into this, right? So the opposite of b over 2a, a is negative here. So those are going to cancel. Or 2, keep in mind what this is, right? This is a side length for this fence that we're building. It's got to be positive. Yeah. So 45 is L, right? What are we trying to find? Go back to the question, which I don't have a copy of. The question was, what is the maximum area that he can enclose? What did we just figure out? What L should be, right? We just found what L, the side that we labeled L in our diagram, the ones that go this way, the ones that there are 2 of. We just figured out that to get the maximum area, this side and therefore this side should both be 45. We don't have the area yet, right? The question was, what is the area? So what we just learned is that this is 45 and this is 45. So what do we need to get the area? Subtract those two to get the other side, right? We had how much fence to begin with?
180. So what's left over for W? 90. Okay, so this thing should be 45 feet by 90 feet, right? Those would be the dimensions. The area then, finally going to actually answer the question, would be whatever 45 times 90 is. $4,050. This would be square feet. Excuse me. These, you'll see this when you get into the homework if you haven't already, but just make sure, and I mean, anytime with word problems, of course, but just make sure that you're answering the question that it asks, right? You're gonna see some of these that ask for the dimensions, or like how long should the shorter side be, or what is the area, right? So just make sure that you're actually answering the question. 4,050. I did it by going back to the picture and figuring out like what the side lengths were, right? So we've got this one's 45, that means this one's 45. That means there's 90 left for the other one. You could also get this if you took this and plugged it back in here, right? This would just be the Y value that goes with that. And you kind of also see here why I've been, I've said a couple of times, like finding the vertex from the graph. Sometimes it's going to be a little bit of a hassle because it's in a weird place, right? If you just like graph that and just zoom out, by the time you can see 4,000, 45 is going to look real skinny. So it's going to be kind of hard to tell like what the graph looks like. It's just going to look like a line almost with like a point at the top. So that's why this thing is kind of nice, because I don't have to mess around with the graph. I can just plug it into that real quick and get what I need. Okay. You feel okay about that? More or less, anyway. Okay. So tell me what's going to be different about excuse me, 7. Yeah. Fence off a rectangular playground. So there's a rectangle. Then divide it in half by another fence that is parallel to one side of the playground. All right, that's kind of a dense sentence. What does that mean? You want to divide it in half, right? That part's easy enough. What about the by another fence parallel to one side of the playground? What does that tell us? Do it. Equal sides, yeah. So it's a rectangle, so there's 2 sets of equal sides. We're building the whole thing because we don't say anything about otherwise. Another fence parallel to one side of the playground. That means you're either going to fence it this way, like cut it in half that way, or this way, but you're not going to go like diagonal or something, right? That's what the parallel part, that's all that is really saying. You're going to go this way or this way. Does it matter which way I draw the picture? Does it matter if I draw the picture that way or this way instead? It does not, because we're not really trusting the picture, right? The picture is just helping us figure out what we're building, how to label things, how to set up basically that constraint equation, the perimeter thing. So it might end up that mine, it looks like the ones that are going horizontal are longer, right? It might end up that these end up being longer. Like I don't care about that part. I'm just using this to think about and kind of frame out how we're thinking. Frame out how we're thinking. So because it's a frame, I didn't even plan that. So what do I need to do? There's 450 feet of fence available. We want to find the maximum area again, right? And the dimensions that give the maximum area. So there's sort of 2 questions here, right? Once we've got a diagram, we need to label it. So what do you think? Okay. So call this W, and this is W, and this is W. And then this L. Works for me. Sides that go the same direction or the same length. Doesn't matter if you use L and W or X and Y or whatever. Just that things that go different directions need a different label. Okay, so we've got 450 feet of fence. And we need to build W, 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 L, and L, right? So three W's and 2 L's out of that 450 feet. That again is our constraint, right? We're restricted to that much fence. And our objective, the thing that we want to actually maximize, is the area. What would the area be for that rectangle? Length times width. Once you're at that point, like the way you actually work through it, the stuff we do is going to be exactly like what we talked through, yesterday and just a minute ago with the other one. Take this, figure out how to write L in terms of W or W in terms of L, and then substitute it in here. Again, you're going to get a parabola with something down, and you go find the vertex, right? The thing that's going to change in these problems, and you'll see, several examples in homework and stuff. The thing that's going to be different is the geometry here. So the number of sides and stuff, which changes this, right? These two things are tied together. The diagram, the geometry, what's going on here gives you the constraint. And then, once you have that, like the process is going to look pretty similar, right? So what I would do here is take this and solve either for L or for W, doesn't matter which. Sometimes one might be a little easier than the other. Here, it's going to be kind of a toss-up because either way, you're going to divide 3 by 2 or 2 by 3. So you're going to have some kind of fraction somewhere either way, right? So it doesn't really matter. And 450, is divisible by both. So 2L is 450 minus 3W. So L is 225 minus 3 halves W. And then we substitute. This is L, not W. I drew my arrow to the wrong place. So and if you want to rearrange that, you don't have to. But that's what that is. Which again, I know coefficients a little messier than the last one, but W squared, so it's quadratic. Leading term is negative, so it's opening down. And what are we trying to find? Maximum, so we look for the vertex. Again, the vertex is just do the negative b over 2a thing to get what W is. You find W, and then you can either go back to this is a good place to look at the question. Question said, what dimensions will maximize the enclosed area? So the dimensions mean find L and find W, right? So you get the W from the opposite b over 2a thing. Go back here and you can find L, or go back here and you can find L. Bunch of places you can find L, and then maximum area just link times W. Link times width. Okay. Okay, so again, I'll leave that one for y'all to finish. There are a couple more, sort of similar things in the homework. Again, this homework for this week, the 3.2 stuff, the big things that you might struggle with a little bit or that need a little extra time or attention are going to be completing the square probably, and this kind of thing, right? Like the projectile motion stuff where you have a function that asks you for the maximum. Hopefully that's not all that big a deal. There's a little bit of interpreting stuff you have to do there, but these I know are a thing that give people some trouble. So again, like finish that, do some more of the homework. If we need to hit it again and talk about it again on Monday, we do that. Okay.
Okay, all right. So
Talk about what solving equations involving some kind of quadratic looks like. Okay, so like I think I said yesterday, I don't know, everything's kind of a blur, but I think I mentioned yesterday that like we're gonna still be working with quadratic stuff until, kind of middle of next week. So we've got a little space for things to, kind of breathe a little bit. We'll have some time to, hit questions and stuff that we need to. But also, like I said earlier, sorry, I don't think I don't like saying it like I said. Anyway, like I said, yes, the jokes write themselves, folks. Okay, so homework stuff. If you haven't already started 3.2, one, you should have. Two, do it like ASAP. And if we need to talk about stuff Monday, first thing we can, or email me with questions or whatever. But back to the test thing and changing your approach and stuff. Part of that is probably going to be getting into homework earlier, right? I don't always keep a real close eye on like who's done what when, but I know that it's not that uncommon for me to look at things on Monday morning and, 2/3 of the class hasn't even opened the assignment yet. So like things are meant to be, it's all building, right? Stuff we talked about Tuesday matters today. And so, yeah, again, my advice would be that, it'd be a good idea to probably spend 30 minutes, an hour or something every day doing stuff, right? It's not that big a deal if you sort of break it up over time, and I think you're gonna get a lot more out of class time too. Okay, so anyway, solving equations involving a quadratic. So we've talked about quadratic functions. Now we're gonna look at what does it mean to solve a thing, right? Solving quadratic equations. So first, maybe just a real quick, second on solving equations in general. If I want to solve something like 2x plus 1 = 5, what do we do? This is not quadratic, right? It's just throwing it back. If you want to solve that, what do you do? Subtract 1, okay. 2x is 4. Then divide by 2. Okay. So solving means if we can just isolate it, right? Get the unknown by itself. Here we do that by just subtracting and then dividing. Okay. So what changes if we're looking at something like x² plus 5x plus 6 = 0? Why is this different? X shows up in two places. It shows up in two places and in sort of a different kind of way, right? They're not like terms, they're different order, x² and a linear x in the first term. So it shows up in two different places. I can't combine them. I also can't isolate in the same way because if I get that by itself, there's still an x somewhere else on the other side of the equation. If I get that by itself, then this x² is somewhere else. So I can't just like push things around the way we did with the other thing. I can't just push things around and get the unknown by itself anymore. Okay, so well, one thing that we can think about is, what if we think of this as a function right? Look at it as y equals x squared plus 5x plus 6. What can you tell me about that before we even graph it? It's a parabola and it opens up. Good. Okay, there it is. We're trying to figure out where it's equal to 0, right? So if I think of this as y equals x squared plus 5x plus 6 and asking where is that equal to 0, what are we looking for on the graph? 0 and x or a y there? What would it mean to solve this equation? Am I looking for, are my answers going to be x's or y's? X's, right? I mean, the answer to this question, this equation would be when x is this or this, right? Or whatever, however many there are. So 0 then I can treat as a y, right? So think about when is y equal to x squared plus 5x plus 6, that's its parabola. What I want to know is when is that the same as 0? So on the graph, what does that mean? Oh, that's just my adorable daughter. What does that mean on the graph? X-intercepts, right? Means where is y 0? Right, it's just like, what was it? First problem on the test, right? Here's a graph, when is it equal to whatever? Here's a graph, when is it equal to 0? Right here. Right, when is it the same as the y value 0? So from the graph, I can, get that that's -3 and -2. Okay, so we know the answers, right? It's x equals -3 and x equals -2. What we're working on is how we can find those, right? What the algebra looks like to sort of verify that. Okay. So, any ideas on things we could do to solve that equation? We know the answers, right? How can we work through, what kind of algebra stuff can we do to work through solving that? Subtract 6? Or factor? Say again? Some kind of ABC thing? So A here is 1, B is 5, C is 6, right? Let's see. If we subtract 6, where are you going to go from there, Brooklyn? No? Why not? Okay, okay. All right, so we think maybe nothing there. Mary, you said something about factoring. Factor how? Okay. X plus 2 and x plus 3. So factoring, you're looking for two numbers that multiply to give you 6 and add to give you 5, right? Which would be 2 and 3. You can think about this a little bit like the completing the square thing if you want. 2 and 3, what that means is that I can break x squared plus 5x plus 6 into x squared plus 2x plus 3x plus 6. Oh, wait. Sorry, I'm getting confused about my color scheme. There we go. And then if this is the first and outer and inner and last parts of expanding a thing, x times x, x times 2, x times 3, and 2 times 3 gives you 6, right? Okay, so when you factor it like that, how does that help us? Why can we set each one of those equal to 0 and solve? Okay, yeah. So, I mean, look at like, what is this thing, you know, sort of big picture. Cover these up for a second. What are we doing here? Multiplying. You're taking one thing and multiplying it by another thing, and what do you get? 0. When you multiply two things, if you get 0, what does that mean? It means that either this one was 0 or this one was 0, right? The only way to multiply things and get 0 is if one of the things was 0, right? If they're both positive, you get positive. If both negative, you get, you know, like the only way to get 0 is if one of them was 0 in the first place, right? Because that's how 0 works. So that's why we can do what Emily suggested and split these up using a thing that we call the zero product property. That's not a Y. Property. If A times B equals 0, then A is 0 or B is 0, right? That's the only possibility. So X plus 2 equals 0 or X plus 3 equals 0. Which again, just like, you know, we saw this with the absolute value stuff a week ago or something. We take this thing that looks complicated and scary, we apply this, you know, this idea to it, and now we've split it up into smaller, simpler things that we're better equipped to solve, right? X plus 2 equals 0, that means X has got to be -2. And if X plus 3 is 0, that means X has got to be -3. Okay, cool. So if we can factor and apply this part is very important, and I'm going to make a big deal about this a lot, and I think you should too. When you do this in your notes, I think you should write this down. Like write that you're applying the zero product property, or, you know, abbreviated ZPP or something. Like this only works if you multiply two things and get 0. That's the only time it works. So can I do anything with that? Can I split those up in the same way? No. Why not? Lots of stuff that you multiply and get 4, right? Even just, you know, integers, like easy answers, you know, are they 1 and 4? Is it 2 and 2? Is it -1 and -4? Is it 8.5? I don't know. Because 4 isn't special like 0 is special, right? That's really what we're you know, basing all of this on. 0 is different than everything else. This doesn't work. I mean, we can still solve this. You would just have to like multiply stuff out and sort of collect things first. Don't worry about it right now. But we definitely can't just break them up the same way we did there, right? Okay, which, Brooklyn, when you first brought up like moving 6 over, if you did move 6 over, you can take a common factor out of these, right? Because they've got an X in common, but it's not really going to get you anywhere because you're not going to be able to split up the same way because 6 isn't special like 0 is. Yeah, good. And I think you caught that, but yeah. Okay. Is everybody okay with that? Okay, so that's one way that we can solve. If we can factor, then we can solve. I've lost my, there it is. Okay, so in the notes, that's this. That's going to be kind of our first check probably for solving. But not everything factors in a nice way, like you, I think, know that from again, I'm sure. Not everything factors in a nice way. When it does, awesome, makes life really easy. When it doesn't, oh well, we gotta move on, right? So what I would say is, you know, by the time we get to like test time or whatever, it's just here's a thing, solve it. get it equal to 0, spend 30 seconds or something, a minute, see if you can factor it. If you can't, move on, do something else, right? So what are the something else's? Here's one. Say I wanted to solve x squared equal to 4. Give him a ladder. I thought somebody said square root. Somebody said square root? I'm just hearing things. Okay. All right, well, what can we do here? Take a square root? Yeah. So how is this different than the last one? There's only 2 terms. There's an x squared term. There's no x in the first term in there, right? So you've got a perfect square here. If you have a perfect square, to get rid of it, you do a square root, right? There's a little bit of a catch though, because remember, we've looked at x squared and the square root before as functions, right? X squared is not 1-to-1, right? That means it doesn't have an inverse quite right, and that's why the square root function sort of looks like a parabola on its side, but it's only half of it. Yeah, we haven't looked at that part before. That's the square root function, right? That's its reflection. If you take those together, it's just like x squared, but laid over on its side, right? But it's both of those things together because x squared is not 1-to-1. So what happens here is that when you do this, the square root and the square do cancel each other, right? They undo each other, but I don't know if the thing that I squared to get 4 was 2, or what else could it be? -2, right? So, okay. So when we do this, you take the square root of both sides, but the thing that you get on the left is not just x, it's the absolute value of x. Because the square root function is defined so that it gives you positive stuff back, right? And if the absolute value of x is 2, what can x be? 2 or -2. Now, most of the time, most people don't write that absolute value step in the middle. Most of the time, we just end up kind of shortcutting that and saying that if the square root of x squared, or sorry, if x squared is equal to 4, then I can take a square root. But when I take a square root, when you decide that you're going to take a square root somewhere to solve something, you pick up 2 things. So you introduce a plus or minus. That's usually how people, will keep track of that or write that. So x is plus or minus 2, meaning it's, 2 or -2. So normally, like it's the same thing, like we're doing the same stuff. This is why the absolute value thing is why you get the plus or minus. I know I'm getting a little bit too mathy here, like I get that. But you get the plus or minus anytime that you decide, like if there's a square root already there, that means the principal or the positive root. That's why when you punch a square root into your calculator, it just gives you the positive one. That's what the symbol means. There's no square root written here to begin with, right? Stuff in blue, that's the written problem. I'm doing the square root to undo a square. Because of that, we have to be careful about the plus or minus thing. Does that kind of make sense? I know that's like a subtle thing, right? But yeah, so if you do a square root somewhere, you pick up a plus or minus along with that. That's the square root property thing. The second bullet point. So that's cool. That's nice. It's convenient sometimes because it lets you do stuff where you've got a perfect square. So for example, if I wanted to solve like 2x plus 1 squared is equal to 9. Because we've got a perfect square already, I can undo that perfect square by taking a square root. But again, if I take a square, if I decide a square root is going to help me somewhere,
it introduces a plus or minus along with that. So 2x plus 1 would be plus or minus 3.
Which splits it into two separate things to work out, right? 2x plus 1 is 3, or it's -3, and then you solve those. Generally, again, thinking about, the shape of the graph of parabola, we're kind of expecting two solutions, right? Yeah. Not always, but that's kind of what we go in expecting. Yeah, we'll get more into that, but most of the time we're going to see two. Okay. Now, like, we know how to force a thing to look like a perfect square, right? You complete the square. That's probably more trouble than it's worth most of the time, but it's a thing that you can do. So like, I can take something and force it down to be a perfect square like this by completing the square, then do this.
Most of the time, there are easier ways to go about it, but it's an option. Okay, so factoring.
Great when it works, if I can get the thing equal to 0 and then figure out how to factor it, then, once we've got it factored, the solving part is, pretty straightforward, right? So that's cool, but factoring is hard in general. So, doesn't really work it's not a like general all the time kind of thing. Square root property, easy enough, right? We got to remember the plus or minus thing, but it does simplify things quite a bit. Again, when it works, but it only works on a thing that's a perfect square. To make a thing be a perfect square, you gotta, so like, look at these problems like 4. 4 would be a perfect place to do the square root property thing, right? Take a square root of both sides because you got a perfect square. 1 would not be a good place to try to do that because you got it in front of you. I just went it. That would not be a good place to try to do it because to make that a perfect square, you would have to complete the square first. That's a whole separate side thing that's gonna be a bunch of work, and then you come back and then you gotta solve still. There are better ways to do that.
So they're both, kind of straightforward enough, but only work sometimes. There is, though, a general method for quadratics.
You probably know it. I'm sure you love it. The quadratic formula.
It's been around for a couple of thousand years. We have a guy named Al-Khwarizmi from
where is he from? Iran? I don't remember, but like 700 AD or something like that. Anyway, solutions of ax squared plus bx plus c. So standard form
equal to 0. That part is important. R x equals. Does anybody remember it?
B plus minus squared of b squared minus 4ac over 0.
My man. Do you actually remember? Did you look it up already?
Oh, I learned it in school.
Okay, yeah, right.
yeah. Yeah, that's it. So you just take the coefficients A, B, and C, you mush them together in this way, and you do some arithmetic, and Bob's your uncle, you get solutions, as if by magic. So this is, unless there's something later I'm forgetting, this is the other place where here's a thing that we just kind of need to know. Like, this is the only other place that I'm really gonna, expect you to like memorize a formula. I hate that too, but by the time we get to taking a test, you're gonna have done this so many times that you'll know it whether you want to or not anyway. You can sing it to the tune of Pop Goes the Weasel or something if you want. Maybe there are other lines. So that's one I like. That Macy's with me. Yeah. All right.
Oh, we got time to do one. All right. You know what? Let's actually go back to the one that we did a minute ago. So I can kind of make a point. So it was the same example. X squared plus 5x plus 6 equals 0. We already know the answers are -2 and -3. Let's do it by quadratic formula. Again, check this part first. Got to have it equal to 0 or the formula doesn't matter. If it's not equal to 0 like that, then move stuff around so that it is. All right, what's B here? 5. -5 plus or minus the square root of 5 squared minus 4 times A is 1, C is 6 over 2 times A. -5 plus or minus the square root of 25 minus 24 over 2. -25 minus 24 is 1. And the square root of 1 is 1.
Plus or minus means that there are really two things there, right?
So I would probably go ahead and split these up.
Okay, pros and cons. Quadratic formula works every single time, no matter what, like you can prove it. Happy to show you that if you want, I'm sure you don't, but you can prove that it works every time. So that's cool. There's no like, it only works sometimes, I can't do it every time thing. The drawback is that it's kind of a medium amount of a hassle, right? Like, basically anything that you do with the quadratic formula is gonna be about this much arithmetic. And I would caution you against like skipping too many steps. Like once you've done a few, you can, I know you can like shortcuts and stuff. Don't do too much because then you make arithmetic mistakes and it, goose things up and you get mad at yourself. Write down 3 or 4 steps in the middle as you're like doing the simplification. So it's always kind of a medium amount of work. But I mean, once you've done it 6 or 8 times, it's not gonna be a thing that takes you a ton of time or effort. So there's that. Yeah, so hang on to notes. We'll pick up there on Monday.
Take a look at, try to work. I don't know. At least try to work number 1 for Monday.
We'll start there. Y'all can tell me about 1 and then we'll spend some time on these others and move on. All right, y'all get that. I'll see you Monday.
Or sorry, good, whatever, weekend. It's been a long week.